Welcome, ladies and gents, to your first note guide of Unit 8. The Unit 8's title is Sequences and Series. This is section 8.1, which is just talking about sequences, not series yet. And we are going to be specifically talking about the explicit rules for sequences, right? You'll see that right up at the top here. There's two main objectives to this section. One, we're going to identify arithmetic and geometric sequences. I realize this word looks like arithmetic. It's not. When we're talking about sequences and series, we pronounce it arithmetic. So arithmetic versus geometric sequences. We're going to also be writing the explicit rules for sequences, which is really looking at a set of numbers and finding the pattern and writing the rule for that. Some people like to use the word formula. I call it the rule. Okay, so down here, let's get some of this vocabulary under our belt because it makes doing the math much easier. You'll notice I again talk about what a sequence is. It is a string of objects, like numbers that follow a particular pattern. So if we say 2, 4, 6, 8, 10, 12, 14, we obviously are talking about the even numbers and we're going up by twos. So that would be a sequence, something that is following some sort of pattern. The individual elements, which is really, really important to understand, that the individual elements of a sequence are called terms. So the very first number in a sequence would be term 1, the second would be the second term, third term, fourth term, and so on. Again, I'll be talking much more specific about that in a moment. We have two types of sequences that I'd like to break down really quick. One is going to be a finite sequence, and what does that mean? It has a finite amount of terms. It has an end. So if you look right over here on the right-hand side, 2, 4, 6, 8, notice there's not a dot, dot, dot. That means this is the end. It's a very finite sequence with only 4 terms. 1 term, 2 terms, 3, and 4 terms. The one right below it, you'll notice, which we call an infinite sequence, is a sequence with an infinite amount of terms, which just means the sequence doesn't end. It goes on forever. So 2, 4, 6, 8, comma, dot, dot, dot implies that it goes on forever with that same pattern. Down here, it says a sub 1 is the blank term. Folks, if you see a sub 1, and that is a subscript, that is going to be the first term. So in this sequence over here, let's right up here, this would be the first term, or a sub 1. This would be the second term, third term, and fourth term. These would be the number of terms. So a sub 4, it would be the fourth term. So 1, 2, 3, 4. If I said, hey, what is the value of the fourth term in this sequence right here? You would say it's 8. If I asked you what is the value for the term, the first term, you would say the value is 2. A to the nth is literally the nth term. So it's going to distinguish wherever in the sequence we're talking about. So if you hear nth, that is really specifying or eventually going to specify a specific location. It's kind of, right now, it feels very general, so just kind of bear with me. I had mentioned up in the objectives, we're going to first really know the difference between an arithmetic and a geometric sequence. An arithmetic is a sequence that goes up by a common value. Difference, a lot of people think of sum or what is being added each time, but we specifically, in arithmetic sequences, we call that the difference, or we'll call it the D value. The difference. So, for instance, the example above where we were going 2, 4, 6, 8, we can see that we are adding 2 to each term. So what does that mean? That means that the difference would be D equals 2. So it's the same value added each time. Geometric is dealing with multiplication. So we have a geometric sequence has a common ratio. So the same value is multiplied each time. So ultimately, arithmetic is dealing with adding, pattern with adding, and geometric is a pattern with multiplication. So if we come on down here, in example 1, let's first of all, start deciding whether or not the sequence is arithmetic, geometric, or neither. If it is arithmetic, state the difference, the D value, and if it's geometric, state the ratio or the R value. So the first thing we're going to do is come on over here. Actually, before I forget, this letter B, we're going to change it. So it's 32, 20. I'm going to just actually change the numbers. It's 32, 27. I'm forcing it to be a different kind of problem. 22. So 32, 27 is fine, but the 21 is going to be switched to 22. Then it's going to be 17, 12, and notice it is going on forever. Actually, each one of these, if you notice, is an infinite sequence. But letter A, the first thing you're going to look at is whether or not, now obviously the values are going down, 512, 128, 32, and look to see if there's a common difference. So I'm going to think to myself, okay, 512 minus 128, that's going to give me 384. If I go 128 minus 32, that is not giving me 384. So this is clearly not an arithmetic sequence. Now, geometric, the fastest way I can show how to decide if it's a geometric is put the second term, 128, over the first term to see if that ratio is going to be the same as the next series. So if I put 32 over 128, that should then equal the ratio 8 over 32. So all of these should have common ratios. Kind of thinking about back to your geometry days, we did this to decide if triangles were congruent. So I'm just dividing 128 by 512. You could reduce it as a fraction if you want. Very quickly, I get 0.25. Oops, I wrote, by the way, 8 over 32. It should have been, or 34, it should have been 8 over 32. Now I'm going to go 32 divided by 128. That also gives me 0.25. And you know what? I already know in my head 8 divided by 32 is clearly 0.25, or in fact these are all going down by a division of 4, if you want to think about it that way. So 512 divided by 4 gives you 128, 128 divided by 4 gives you 32, and so on. Now, so the first thing I'm going to write here is that we do know it's geometric. And the next thing I'm going to say is that the R value, now we know it's divide by 4, but because we're always talking in terms of multiplication, that is the same thing. Dividing by 4 is the same thing as multiplying by 1/4, or this value right here. So you'll notice that I find the common ratio very quickly by doing what I just showed you, which is taking the second term, putting it over the first term, or taking the third term, putting it over the second one, and so on. So this, though, right here, folks, is the answer. Geometric, and the common ratio is 1/4. So letter B, after you've made the edits that I've mentioned, now we're going to actually decide whether it's a geometric, arithmetic, or neither. Looking at it, 32 to 27, again, this is going down. Let me see, I would subtract 5. If I subtract 5 from 27, would I get 22? Yep. And if I go 22 minus 5, would I get 17? And the answer is yes. So what I did for letter B is actually made it into an arithmetic example, because otherwise what would happen, well, I just wanted a good example in your notes of arithmetic. Arithmetic. Oof. Oof. I can do better. I can do better here. It's just does not look good. Okay, arithmetic. And the common difference, what you're adding each time, I know we call it the difference, but what is the difference each time? It's -5. We are subtracting 5 from each one, so we're adding a -5, if you want to think of it that way. So this right here, ladies and gents, is your answer for letter B. Letter C, we have 1/2, 1/3, 1/4, 1/5, and you can look at the denominator and say, you know what, I can see that I'm adding 1 to each one. But really, folks, we are focusing on a full term, so if I go 1/2 plus 1, that is not going to give me 1/3. So if you go and think about what you can do to that whole value of the first term to get to the second one, you are not going to be able to add or subtract any one specific value. So I'm just letting you know that when you add 1 to the denominator versus the whole thing, that's hugely different. So this is not arithmetic. If you take 1 divided by 3, or 1/3 divided by 1/2 to see if there's a common ratio, you're going to end up with the first one is 0.666, which is 2/3. And if you continue to do that, so if I go 1/5 divided by The next one is definitely not point or 2/3. It ends up being closer. Actually, it ends up being 3/4. So there is no common ratio there as well. This is a classic example, and I want to say it's a classic example because you'll see it even comes up in the note guide again. But this is a neither. This doesn't follow either the arithmetic or the geometric patterns. So this is a neither. So anything that has a pattern but it isn't specifically a difference or a ratio goes into the neither category. Okay, so that's how you determine whether or not it's geometric or arithmetic. So really geometric has a common ratio or something that you're multiplying each term by, and the arithmetic is all about addition or adding a negative number, which is the same thing as subtraction really. Now let's talk about how we come up with the rules. So it says explicit rules for sequences. An explicit rule is a function to describe any term based on its position in the pattern. That's very, very fancy verbiage. But really, it's really especially arithmetic, it's bringing up the idea of y-intercept, slope. It's kind of connecting right to your linear algebra. And geometric rules completely are related to your growth and decay that we just got done doing. So let me just kind of talk about the arithmetic first of all. So this is a rule, or this specifically is a general form of the rule that I will give you in advanced algebra. We give these to the students, but in pre-calculus we expect them to be memorized. This a sub 1, it stands for the value of the first term. So let me just kind of describe each of these variables so you know what each one means. So it's the value of the first term. The n, notice there's no a sub n here. This is just n. This literally means the term number. So are we talking about the first term, second term, third term? That's the term number. And the d, as you can imagine, is the d value, or that difference that we talked about up above. So that is the explicit rule for arithmetic. And what I think I'm going to do, rather than getting into the, I could go through each one of them, but I think I want to first just focus on that arithmetic explicit rule first, so you kind of have that down before we throw the geometric at you, even though you'll see that there's a lot of connections to prior math with actually all of these. So I'm going to end up scrolling back up to those rules, but right here, example number 2, it says state if the sequence is arithmetic, geometric, or neither, then write a rule for the nth term of the infinite sequence. So you'll notice they are all infinite. And when it says write a rule for the nth term, it's just saying, hey, you know what, write a rule that will work for any term along the whole infinite line. So I'll just tell you, here's a trick, or I'm just letting you know A and B ends up being arithmetic, C and D is geometric. So we're going to end up just focusing on A and B to start with to get our field for this arithmetic explicit rule. So if you look at that general rule, what you do need to know is you need to know your very first term. You need to know your a sub 1, which obviously the very first term value here is 32. And maybe what I'll do, just because it's up there and I like making sure I can connect with it, I'm going to write that general form right here of that explicit rule. Trying to write it really nice and neat for y'all. Times D. Okay, so looking at this, I need to know the very first value, or the first term value, and that's 32, we got that. We need to know the term number. And, well, actually, let's not talk about that for a minute. Let's first talk about the d value. So what's happening each time here? We are going down, as you notice, value. So we're going to see, are we subtracting, it looks like -5 here each time. And so when I was saying we need to know our n value, I'm already thinking about section 8.3, which is sums, summation. So just kind of ignore what I had just said there. And we know it's an arithmetic. Actually, I'm going to write that up here. Arithmetic. Okay, so that's an E right there. That's lovely. So state whether the sequence is arithmetic, geometric, or neither. So we did that. Then write a rule for the nth term. So you should have an n in the actual rule. So we're going to start with a sub n equals. The very first term is 32. That's where we're beginning. Plus n minus 1 should be written just like that, times negative 5. Folks, this is how easy it is. So once you know your difference and your initial value, which is your a sub 1, all you're doing is putting into your formula per se, and then you're going to simplify it because obviously we don't want to leave it in this form. So distribute that negative 5 through that parenthesis. So we have a sub n equals 32 plus negative 5n plus 5. So we're just doing a little bit of algebra here. So the distribution of that negative 5, then combine like terms, we end up with a sub n equals negative 5n plus 37. Now I'm going to just, this is the answer then. So we have, this is our rule for any term in this sequence. And we know it's arithmetic, so we're going to circle that too. That was part of the other answer. So at this point, if I want to know, I don't know, the 100th term, all I'd have to do is put 100 in for n, and it will give my value at the 100th term. Now think about this. You've seen these kind of equations before. If I substitute a sub n for y, or put y in there, and put x right here, hopefully you're going to be like, ooh, yeah, I've seen that a lot. That means the y-intercept is 37 and the slope is negative 5. So an arithmetic is in fact connected to a linear equation. So that is all we've done really, is the negative 5 was the slope of the data. And really we took it, because we're dealing with the first term and not the 0th term, so you need to take it a step back to get that y-intercept, which is 37. So I am showing you a very algebraic, very, very traditional way of doing this, but I'm letting you know there's more than one way to find that equation. Just know that what you have to give me in the end is what I put in the cloud, okay? So arithmetic, and then that a sub n equals negative 5n plus 37. And if you want me to show you some shortcuts, I can, but part of me feels like I just need to first make sure that you know how to set these up very traditionally. So starting with letter B, notice that this, we're actually going up, we're adding or increasing our values. I kind of already told you it was arithmetic, which I probably shouldn't have done, but arithmetic. And the D value is, I don't know, we're adding, what, 6 each time it looks like? And so, and I know my very first term, a sub 1 term, is negative, the value negative 15. So folks, this is where you're plugging and chugging. If you don't want to really use any common sense, you could just literally just put it in, not even think too much about it. So what do we have? We have negative 15 plus n minus 1 times 6. And then simplify it really quickly to get it in that, if you want to think of it in slope-intercept form, you end up with 6n, what do we have there, minus 21. So that right there, folks, you would need to be able to give me, and obviously this right here. So that, again, is the explicit rule. That rule will give you any value along that infinite sequence. So again, if all of a sudden I was like, hey, I want to know what the 1000th term would be, you throw it in this and you'll get your value. Okay, so that is arithmetic, how to find the explicit rule for that. Now let's talk geometric. And I really like the geometric because, especially since we just got done doing growth and decay, it's going to be like, oh, that totally makes sense. I'm just going to first make sure you remember when we were doing growth and decay, a, b to the x. We kept doing that over and over again. The a right here was the initial value. Folks, this is the initial value, or again, the value of that first term. So I like kind of getting that idea. It is the initial value of the first term. The b right here is your growth or decay factor, and you know what? That is exactly what the r is. The r is the common ratio, which is just the growth or decay factor. And the n minus 1 is, again, without getting too convoluted, I just want to explain the reason why it's not to the nth power, or n, it's n minus 1. The whole reason being is that when we start counting terms, so if I go, I'm going to do an arithmetic because it's easier. I'm going to just go do that 2, 4, 6, 8, 10, and so on. This term number right here is the first term. This is the second term. It's not the 0 term. So that's why we have to do that n minus 1 to get it back to 0. So it's like we're shifting it over 1, if you want to think of it that way, with using that n minus 1. So I find students that is a point of confusion for them, and until they kind of get used to it, it does cause a little bit of angst. But I do want to make sure you realize that this is the growth and decay factor, or the growth and decay general formula, just like we did in the last unit. The n minus 1 is the only different thing, and that's only because of the whole shifting of the sequence itself. Okay, so by the way, neither, of course there's a neither. If you get a neither, to come up with a rule, you're just going to either give the sequence, or the rule that you can use, what you can do with the term to get to the answer. And we'll have a couple of those, so I'll kind of give you an example of that as well, obviously. So let's come back down here into those examples. So looking at letter C, we have 512, 128, 32, 8. The pattern clearly, if you look at it, is that 1/4, so, or divided by 4 each time. So I know it's a geometric. So that's the first thing you need to say according to the rule, or to the instructions. Then to make it a little bit easier, I'm going to just say, hey, the ratio, again, you're taking the second number, putting over the first number, and simplifying it. Really, that's what's happening. Of course, I don't like using these big numbers, so I'm going to go 8 over 32, and that's giving me 1/4. Now, of course, we had already done this in that other example, but it's not a bad idea to bring it up again. A sub 1 is that first term value, which is 512. So it's not a sub 0, it's a sub 1. Again, that's why that n minus 1 has to be placed in there. So now let's put the general form in there. A sub n equals the a sub 1, the initial value, times the growth factor, or in this case, the ratio, common ratio. And then again, instead of just n, it's n minus 1. So the explicit rule is going to be as simple as going, hey, there's my initial value 512, I have a growth factor of 1/4 because we're dividing each time by 4, and you leave the n minus 1 because that is going to be what you put in to find whatever value you want along that sequence. So again, if you want to find the 1000th term of this sequence, you put 1000 in for n, and then you get out the value. Or you can go reverse. You can put in the value for a sub n to figure out the term number. And then, of course, we know we'd have to use logs to do that, because that's the only way you can get that exponent out of the exponential spot. By the way, that is done in pre-calculus. We don't do that in advanced algebra, so that's something to look forward to. Okay, so letter D. Again, if you look at it, you can again find the difference pretty quickly by taking the second term, putting it over the first term. I'm choosing that because it's smaller numbers. I like that. And 28 over 14 is going to be clearly 2. So really, or you could just say, hey, you know what, I can see that I'm multiplying each term by 2 to get to the next term, and so on. This is geometric. So that is part of your answer, and I should have circled that because that is part of the answer up here. So that's part of our answer right there. And now we have a sub n equals the initial amount, which is 14, times 2 raised to the n minus 1. And again, that 2 is your growth factor, or in this case, your common ratio. Okay, so those are 2 examples of how to find explicit rules for geometrics. So you can imagine the last 2 probably are the neithers, right? And notice that this is exactly what we had looked at in that example earlier in this note guide. If we say this is term 1, this is term 2, 3, 4, I'm going to write neither right now so we can get that out of the way. But what we want to figure out is, okay, a sub n equals, what do I do to get the value each time? So I guess what I'm saying is that notice how if you start with your first term here, the actual term value 1, or the 2-term number 1, if you take that and add 1 to it, you get the 2. If you take this term number 2 and add 1 to it, you get the 3, and so on. So really, if you take the term number and add 1 to it, you will get each one of your values. So Again, the first term you put in, you end up with 1/2. You put 2 in there, you get 1/3. You put 3 in there, you get 1/4, and so on and so forth. So that is your explicit rule. It's obviously not as straightforward as the arithmetic and geometric, which we tend to focus on, obviously. But with that said, it's really good to be able to make a pattern or an explicit rule for not just arithmetic and geometric. So in those cases, you need to look at how the term number can be written so that you can have make the rule work. So letter F is a neither as well. And if you're not sure why that's the case, now you obviously if you start trying to add a certain value like 9, you can't just keep adding 9 to each thing here in this one, so it's not arithmetic. If you put 27 over 8, that's going to be a different ratio than 64 over 27, which is different than 125 over 64. So you need to test your different sequences to see if it's arithmetic versus geometric, and if it's neither one of those, then you write neither. But that doesn't mean you don't have to write your rule. So this here, actually I should have probably put that a little lower because I'm going to need a little bit of workspace. I'm going to put neither a little bit lower here. So I'm going to put the term number right, should I put it below? Yeah, actually I'm going to put it above it. So this is term 1, 2, 3, 4, and so on. Now, something to think about is that, if you start thinking about numbers, these look like cubes, they are cubes. So like for instance, 8 is going to be 2 cubed. I can rewrite that as 2 cubed. 27 is 3 cubed. 64 is 4 cubed. And this one isn't so straightforward again. This is sometimes hard to see, but if all of a sudden you had perfect squares, all of a sudden 4, 9, 16, and so on, you could do the same strategy where you rewrite it so that they're in terms of cubes. And now, again, notice that this 8 is using the base 2. And even though that's the first term, we can force it to be the second term by going n plus 1. So let me show you what I'm talking about. So I have a to the a sub n equals, if I take the term number and add 1, just like I did in letter E here, the example E. So this first term, if I add 1 to it, so it'd have 2, be the value 2, and then if I cube that, I will get the value 8. If I put 2 in there, 2 plus 1 is 3, 3 cubed gives me 27. 3, so we're writing these explicit rules in terms of the term number, and that's kind of messes with people's minds, but really I've got to tell you, there's just not very many examples of them. I just showed you the 2 most popular ones. So just kind of as you get through them, just kind of keep looking at them. You get better the more you do them. And again, I can show you all sorts of tricks, but at this point I think this is plenty for you. Okay, so example 3 and 4, these are a little different. Example 3, by the way, it should have at the very end say write the rule. Kind of just all of a sudden just doesn't say anything, which is kind of weird. But it says one term of an arithmetic sequence is a sub 11 equals 41. So that means you could have listed all the terms all the way to the 11th term, and I know the 11th term, the value is going to be 41. It says the common difference is D. D is equal to 5, so that's really helpful. So I know it's arithmetic because it states it. I know the common value, or the D value, is 5, so that's very, very helpful. And I know that the 11th term in the sequence is the value 41. Now, if you want to create an explicit rule, you need to know what the first value is. So so we need to figure that out. So here's what I'm going to do is, in this case, I'm going to first just put the explicit rule down, the general form anyway. A sub n equals a sub 1 plus n minus 1. And again, remember, I give you these, I don't explain what each one means, but these don't ever need to be memorized. You just need to very, very much know how to use them. Now, the reason I'm writing this down is that I don't have a sub 1. I'm missing that. I do have the D value, which is good, but I need a sub 1. I need to know what value a sub 1 is. And of course, you can kind of work backwards, although that gets a little tedious. Especially, this one isn't impossible to work backwards to that first term, but if I say, hey, a sub 131 is equal to 5,000, you're definitely not going to want to work backwards from that value. So what I am going to say is, with this, I know that a sub n is 41. I don't know a sub 1, that's what I'm trying to find. Plus, I know that the value 41 happens at the 11th term and that the common difference is 5. So what I've done is I have put in an xy point or an xy value or in this case, my independent dependent value. I actually put in so I could find my initial amount. Or again, when you're dealing with linear equations, this is where you would plug in a point on the line to find your y-intercept, to kind of try to connect it to something you're familiar with. So really, once you have that, so this here was the magic, this is the magic value or information right here. So once you have that, you can just work to solve algebraically your a sub 1. So you have 41 equals a sub 1 equals 10 times 5 is 50. So very quickly we can say that my a sub 1, rather than having to trial and error it, I know is -9. And once you have that, it's just a matter of now throwing it in for the answer, which is the actual rule. So a sub n equals -9 plus n minus 1 times 5. And then you simplify it, and you will end up with 5n minus 14. So that, my fine young ladies and gents, is your final answer. So this one is a little bit more algebraic. So you have to first find your a sub 1 algebraically by inputting in the 11th term and the value at that term, which is 41. Solve for a sub 1, and then you're right back to where you were at the previous examples, where you can just put in what you know, which is your intercept and your slope, essentially. Okay, so this example number 4 is kind of similar. It says one term, although we're talking about geometric here. We know that the term a sub 3 is going to be -18. So just to kind of, again, if you're kind of missing what I'm saying here, is we don't know this term, we don't know this term, but we know the third term is -18. And we do know the common ratio is 3. So we know that the third term is -18, common ratio is 3. And this is clearly something, again, you could work backwards pretty quickly on this one, because you could divide -18 by 3 to get -6, and then again divide that by 3 to get -2. So I'm telling you that in this case, for sure, I would just work backwards just to fill those in super fast. But that's not going to help you at all if I give you like a sub, I don't know, 3,500th term is equal to whatever, and you have to actually find the initial value then. So I need to definitely show you algebraically how to do this. So this example I wrote because I wanted to be able to do this right here, so you can physically see that the third term is -18. But then I worry that people are not going to follow what I'm saying now, and I'm just telling you you need to. Okay, so here's what as I'm talking, a sub n equals a sub 1 times 3 to the n minus 1. Now, this is just the general form with the added common ratio of 3 in there of the geometric sequence. Now, I know that the third term is -18, so I'm going to put -18 in for a sub n. I don't know my initial value, that's my whole goal here, times 3 to the, and again, this is the third term, so I put 3 in for n. 3 minus 1 is 2. So then I can solve this super fast. 3 squared is 9. -18 divided by 9 is going to give me -2, just like I would have figured out by working backwards. But again, the working backwards doesn't work very often because teachers don't write them like that. So just kind of keep that in mind. So algebra, use the algebra to solve for the initial value or the first term value. So a sub n equals, now I'm coming up with the answer here. So a sub n equals -2, which is the initial value, times your growth factor or your common ratio times n minus 1. And that is how easy it is. Okay, so taking a step back again, so you now know how to decipher between arithmetic geometric. You know how to find the d value of the common ratio r value, and now you can come up with patterns or rules for those patterns in the sequences. Thank you for tuning in. If you have any questions, we'll answer those right in class. Take care.